That's good. Yeah. I was just waiting for you, not the time at all.
I know, I appreciate it. Oh, I can.
So, unfortunately, I don't have your quizzes back, obviously, because I wanted to finish the additional example set last night instead. So that is up and ready to go. It's surprisingly long, but rather more than examples are not enough, I suppose. So we are in our last module. That's the good news.
Yay!
The bad news is it's fractions. Because we have to talk about fractions. So the first one is just an introduction. Some of it, if not all of it, will be very simple and very familiar. But we have to start at the right place. Maybe you haven't thought of a fraction in 10 years. Who knows? And we have to start at the right place, even though it starts out very simply. I want to just be more aware of the little things, especially the relationship between the different kinds of ways to introduce and understand a concept, from the intuitive side to the, what should we call it? Yeah, sure, mathematical side. Because in essence, math is about explaining a concept that doesn't rely on my feelings or my mood or my magical insight or something. That systematically, explicitly defines and explains a concept. So there's this back and forth when I introduce a concept, depending on its complexity. How easy is the intuitive side? Sometimes we'll see very quickly that the intuitive side is totally fine in the beginning, but numbers get bigger, things get more complicated, and then I can't be stuck on the left. I have to be flexible and move over when it's necessary. And I find many people, they can explain a simple concept with small numbers intuitively, and it works, everything's good, everyone's happy. But as soon as things get a little more complicated, not even a lot, a little bit, they're stuck here and they cannot make sense of how to think about that concept because they're not able to move over as necessary. So I want to keep this in mind as we go. But that's only going to come in when we look at fancier operations. Right now, talking about a fraction, it's a very intuitive concept in that I can define it loosely as one whole divided into smaller parts. Now, yet again, the yellow book needs updating, so I want to write these out so your notes are complete. I'm going to represent my fraction with what we call a numerator and then a denominator. So, for example, if I have 1 over 3, we say 1/3, and we can represent an intuitive concept, usually goes along with a diagram or something to visualize what is happening. So there is my rectangle. That is going to represent one whole piece. A third of it is just a little portion of the whole. So it's just going to be one of the pieces when I divide the whole rectangle into 3 equal pieces. One whole divided into smaller parts. and the numerator tells me how many of those parts I want. All right. We have a mixed number, or a mixed fraction. Where I have a certain number of wholes with an extra little fraction part. For example, if I have 1 1 with a diagram, I have one whole and another third of a whole. 1 1/3. Very simple, very intuitive, and a diagram makes it perfectly clear, I think. So, yeah, that's fine. 2 3/5. Can you make a diagram? Now, you don't have to feel restricted by rectangles. I do rectangles because I can't be consistent with circles. They get all wobbly and different sizes and it's a whole mess. So I like the rigid aspect of a rectangle. So I'll stick to rectangles, but you can take any shape you want. And a rectangle is easy to divide into equal pieces, visually as well. So I have one whole and another whole rectangle, and then 3/5 of a whole. So now I've divided into 5. Doesn't have to be perfect. Clearly this is, it's not bad. 3 of them. 3, 1, 2, 3. 3/5. Piece of cake. When I write, let me just check, is this even on the camera? Yes. When I write a mixed fraction, I can also write this, let's say here, can also write this. This is a quantity that we're representing with a number or a combination of numbers now. Write this quantity as counting the fifths instead. So in this whole rectangle, this first one, I have 5/5. Then I have another 5 and 3. So I have 5, 10, 3 is 13. So I can always also write this as 13/5, or 13/5. And then we'll call this an improper fraction. Now in school you love your mixed numbers. It's all mixed numbers all the time. Because it's intuitive, you count in wholes and then a little fraction. But eventually mixed numbers are just a little inefficient in terms of their presentation. So you have to be able to go to the equivalent improper fraction. But they represent the same quantity. Same quantity. So I only have a numerator and a denominator, not a whole integer portion. Let's look at a couple of examples. 1 1/3 is what in as an improper fraction. Make the diagram. It's a good habit. We want to be forced, we're not be forced. We want to force ourselves to have clear diagrams. Because that's how little Timmy's going to learn one day. He's going to learn visually, probably. You might have the manipulatives and put things together and make the pizza or the rectangle or whatever. That's a pizza. It's enormous. I just can't do the slices of a round pizza very, very accurately. But it's still pizza. You have to be able to draw it accurately. Because I want to explain it eventually. It's not just me, oh, I can do that easily, yeah. But can I explain it to little Timmy to whom this is an extremely foreign concept? No, initially, but intuitively it makes sense. So I have one whole and another third of a rectangle. So that's what I have, my shaded region. If I count thirds, then I have 1, 2, 3, 4. So 4 thirds. Nothing to it. Nothing to it. If I have, what's this, 2 and 3/5. 2 and 3/5. Take them, no less than a minute. Take some time, draw the quantity, represent the quantity graphically, so that little Timmy can see what the improper fraction is.
You just did that one.
No, did I? I'm sorry. Problem solved. It appears a few times in my notes. I don't know why. So yes, I know it's very simple, but to the right audience, it is not. And why do you think, if you ask kids in general, there are a couple of things in math that they'll use the word hate. Fractions is one of them. Why do they hate fractions? Why?
Complicated?
Why is it really complicated, or is it all in the presentation?
Yeah. Teacher hates it.
Maybe a little bit of both. Sure, compared to integers, of course it's more complicated, relatively speaking. But with the right presentation, I really don't think it is. That said, I still remember, sort of vaguely, I have this image in my head when the teacher introduced fractions for the first time. I had no idea what he was saying. Not a clue. I remember the image. I was sitting on the right side of the room. Not a clue what he was saying. Made no sense to me. Because he just started writing fractions on the board. We didn't know what he was talking about. It's all in the presentation, which is true for many things, many things. So I have one whole rectangle, and let's shade that in, and 4/5 of a rectangle. Get used to dividing into thirds, fifths. We'll get to sixes. There's a lot of sixes in the additional example for some reason. I saw last night. Who knows why? I was writing the one page for the answers, and I wrote one question out, the answer, and then I left to go to the kitchen. I can't remember why. And then my 5-year-old decided, oh, I'm going to do what Daddy does, and started doing little rectangles as well. But of course now I can't use it anymore. The rectangles weren't bad, but she didn't know what she was doing. She was just starting to draw rectangles. Like, now I have to redo that one. She just wanted to contribute. So can't get mad at that. So I have, if I'm counting in fifths, 1, 2, 3, 4, 5, and 9. She was also very fascinated by the whiteout, the little tape whiteout, the little roller that you just sort of pasted on. Fascinated by that. She just wanted to white out everything. Like, no, it's not going to work. So, these numbers are small and easy, but they do suggest a more general rule. How do I get to the 4? So I'll rewrite this here. Let's see, we observe a pattern. When we do a couple of these, and of course little Timmy will do more than just 2. Intuitively, with a diagram, you get the answer. But when the numbers are big, and I give you something like 23 and 9/17, yes, I can do it. No, I don't want to. I want to use small examples to come up with a pattern and a rule. Yes, it's inductive reasoning, but it's sort of guided inductive reasoning that the pattern is the correct one. How do I get to this 4 using these numbers? Well, look at the diagram. The diagram suggests it's one whole, so one whole group of 3. So let's just change let's change it so that the 1 and the 1 aren't the same. Let's make that a 2, just so all the numbers are different. Then this will be another third that I get, and I have 5 over 3. Now all the numbers are different. Easy to keep track of them. So how do I get this number? One group of 3 plus another 2. That's what I did with the diagram. Graphically, that is exactly what I did. Here, all the numbers are different, so I'm good. We, or little Timmy, got 9 over 5 by counting fifths, just going 1, 2, 3, and so on. But there is a pattern that he'll eventually observe. It's one group of 5 plus another 4. So if I were to do 23 and 9/17, I'm not going to draw the diagram. I'm starting to cross over, seeing, I don't have to say inductive reasoning, but that is what I'm doing. Inductive reasoning is moving me over to the general mathematical property that tells me how these are equivalent. It'll be 23, if I were to draw 23 whole rectangles containing 17 17ths each, plus another 9. So there's a balance between, this is really really this is the theme of the whole module when I think about it more and more. The crossing over from intuitive to, how should I say, I don't say mathematical, I can't come up with a better word. From intuitive to mathematical, where little diagrams, and they can find the answer without having any understanding of what's happening. But eventually, the numbers won't allow me to do that. And I want to notice patterns, come up with properties that enable me to sidestep the whole diagram. Moving over. I don't want to be restricted just on the left or just on the right. If I'm just on the right and know everything mathematically, I can't explain anything to little Timmy. It's a movement between the two, a flexibility. Mixed numbers, right. Let's then go the other way. Given an improper fraction, how can I, let's just say the rule explicitly here. So this leads to the general, whoops, sorry, that got out of hand. General rule. As little Timmy doesn't have to know. He'll actually come up with it on his own. If I have A as the whole and B over C as the little fraction, then that is, I'm counting fractions based on C, A groups of C plus B. You're not going to show little Timmy that. In fact, I'll avoid it on purpose, because as soon as you show them a formula, all thinking stops and they just plug and play. That's not what you want. You want the understanding. But secretly we know how these are related. For when numbers get bigger, you have to rely on that. The other way around. So yes, the topic is simple, but I have an ulterior motive. I have another goal in mind that prepares me for my possible career. Let's go. Do I have examples in my book? Yes. I don't need that big. It's too big. 8 over 3. Now, intuitive only. I'm counting thirds. 1, 2, 3. Okay, I have 3 thirds so far and makes a whole. Then I'm counting, there's another third, and another one, making another whole. I have only 6 so far, I need 8. So I make another third, and I'm done, but that's only a part of that rectangle. 3 thirds make a whole rectangle. But I can clearly see that that's 1, 2 wholes, and 2 thirds. No understanding necessary. And it's a good place to start for sure. I'm going to come up with another example. I don't know, example 9/4. So I have fourths here. I can do 4, and that will fill one whole rectangle. I need to get to 9. Well, let's just be lazy and make it 7. That one had 2 holes already. I don't want to make them too similar. So 7, I need to get to. I have 4 already. So only 3 fourths in the next rectangle will get me to 7. So clearly I have 1 and 3/4. Nothing to it. But then again, if my numbers get bigger, and I have to look at, whatever, 37/8, and this is a lot of work. The rectangles will still work, but it becomes inefficient, and I don't need to stick to that left intuitive side that closely. So what do I see here? How do I get these numbers? All right. I'm just writing this in reverse. So now I have the 5. I'm thinking quotient and remainder. So if I do it on the side here, 8 divided by 3, 3 goes into 8 2 times, 2 times 3 is 6, take it away, I have 2 left, so it's 2, remainder 2, my quotient is 2 as well. So I can write 8 with the quotient and remainder as quotient times divisor plus remainder. The quotient is the number of holes, the remainder is the numerator of the little fraction that's left. I'm just doing this in reverse. What we get here, I'm going to divide 7 or 4 into 7. 4 is into 7 once. 1 times 4 is 4. Take it away, I have 3. So the quotient is 1, remainder is 3. So 7 can be written as quotient times divisor plus remainder. So that 1 is the number of holes. That 3 is the the numerator of the fraction that's left. So my general rule, where can I put that? Over here. General rule for when things get a little inefficient to draw. I'm noticing a pattern. I'm moving over to the mathematical side. Oops. General rule. If I have, how should we write this? If I have an A over B with A greater than B, that's an improper fraction. If the numerator is too big, or bigger than the denominator, then we write A as Q times B plus R, quotient, remainder, and then the mixed number version will be quotient as the number of holes and remainder over B. So it gets a little maybe confusing or messy when you want to write a general rule. But whether you understand it sort of without specifically saying it, or whether you write it out, there is a rule that is explaining how these things are linked. So in this case, 37 can be written as 4 groups of 8 plus 5. So that will be 4 holes and 5 eighths left. So noticing these general properties help me to do things faster, help me to handle more complicated situations. But initially I start with a very intuitive, low understanding way of introducing the concept. But I have to be able to move as the need arises. Any questions on that? Everyone sort of understand what we're trying to do here? The topic isn't complicated, really. We all know how to work with fractions. But we're just thinking about this a little bit. About little Timmy. About how to introduce things and the pros and cons of different approaches. Do you just throw a rule at Timmy and say, just use it? Stop asking me questions. Or do you stick to an intuitive side completely? Or do you drift between them as you need to? All right. Next on the agenda, let's note different ways of writing fractions. For example, if I have a half, I can represent that with my whole rectangle and I am using half of it. Pretty simple. What I can also do is split that sideways in two, sure. And now I'm counting, I've divided the rectangle into 4 equal pieces. So I'm counting fourths, and I have 2 of them. So these two are the same. It represents the same quantity. It represents the same quantity, so we say 1 over 2 is equal to 2 over 4. People forget. I see it every year. People forget what the equal sign means. What does it mean? No one knows, really. No one thinks about it. It means that these are equivalent ways of representing a quantity. There are different ways of representing the same quantity. We say they're the same. The quantity that they represent is the same. I can also take this 1/2. There it is. And split it sideways into thirds. Now I'm counting 6 pieces in the whole. And I have 3 of them. So we say that those 2 representations are equivalent or equal. And I can do this for any number. What have I really done? I had my, let's go original here. That was my original one, right? I had 1 out of 2. What did I do to these numbers when I split it up sideways? I decide on a split of 3, then I created 3 pieces. So I've timed the top by 3, and overall I've split the whole thing into 3 pieces, and I've multiplied that, or timed it by 3 as well. So this general, this is the same as 1 times 3 over 2 times 3. This is the original 1 times 2 over the original 2 times 2. And I'm not restricted by what number. The only thing is they have to be the same, because I'm drawing my lines throughout the rectangle. They have to be the same number. They're multiplying these in the same way they're multiplying the whole original 2 halves. So this leads to a general rule that if I have my fraction a over b represented as a rectangle, but I'm not restricted to nice simple numbers anymore. I can take any other number c as long as I multiply it on both sides. So even if the numbers get really big and my rectangle falls apart or is inefficient, I can take, whatever, 21 over 47, and that'll be the same as 21 times, can we do a 3? We've done our mental multiplication. 21 times 3, 63. 47 times 3? We're not restricted to Mondays. We have to do it anytime. Anyone?
141.
141. Am I really going to split a rectangle into 47s? No. It's ridiculous. I don't even think I can do that. So I take simple examples, notice a rule, and when the need arises, move over to that side of my concept. More importantly, more useful, I suppose. Why would we make a simple fraction more difficult? No. Is the other way. It says that, I know I'm saying the same thing, but if I have a fraction, and I see the numerator as two numbers multiplied together, and the denominator as two numbers multiplied together with the same number used, that is equivalent to the fraction of the first numbers, just using this backwards. Equal means they're the same. So I can use them in either direction. Which we see this, or say it, as canceling. Does that mean 2 out of 1? No. I'm doing math, I'm not spelling. Canceling, let's just say loosely here, the C number. Canceling. Now notice how this came from making lines horizontally, which caused multiplication, and nothing else, multiplication. It was a result of this line making that I'm multiplying it. So this is always multiplication. Always multiplication. Which means that C is a common factor of the numerator and denominator. And I see this canceling common factors. But it comes out of something very simple. Something very simple. Only multiplication. It has to be multiplication. So then if I take an example where I want to simplify 72 over 100, I just need to break up the numerator and denominator into multiplication, and just two numbers at a time would be fine. I see they're both even, so I can go 36 times 2 and 50 times 2. By that property, that general rule, this is the same as 36 over 50. The numbers are bigger, the rectangles won't work as well, but the principle, the concept is the same. Then I can go, oh, they're still even. So I can go 18 times 2 and 25 times 2. So that'll be the same as a fraction with smaller numbers, but an equivalent quantity, just without the horizontal lines. Still dividing the whole into the same pieces. Can I do any more with that? It doesn't look like it, but how do I know for sure? If I look at the prime factorization of 18, it is 2 times 9, so it's 2 times 3 squared. And 25 is 5 squared. You see, they do not come from the same building blocks. They do not have any prime factors common, so they can't have any common factors. Not that you have to tell little Timmy that, but we know a little more. Little Timmy will just guess and check and conclude that, no, we can't find anything. But we know why. They're not both from the same numbers. So we say that this, I think there's more than one way to say this, but I'll just say this is in simplest form. I'm sure there are other ways to say it. When I can't reduce it, simplify it anymore, there are no common factors, then it's in simplest form, or simplest terms, or something simple. When the numerator and denominator do not have any common factors. And factors, this means, whoops, multiplication is the only thing working here. And if you don't emphasize that, or if you're not sort of overly aware, then kids can do strange things. Only multiplication. So then, Timmy sees the teacher do something like this. And they're right on the board. Oh, 2 plus 2 over 1 times 2 equals 2. Now, without the proper guidance and explanation, he can make the conclusion or observe a pattern or a rule from this example, and you just rewrite this and saying, oh, the teacher didn't really say, so I guess I just cancel these guys and end up with 2 over 1, which is 2 wholes, which is 2. So that must be the way to do it. Not understanding that the canceling of common numbers are only common factors, meaning multiplication. Is this true in general? Is this pattern true in general for any choice of numbers? Is that the right conclusion that he made? Is that always going to work? No, of course not. But can I show an example where it's not going to work? So something plus something and something times, and this has to be common, but the cancellation doesn't work. Can I come up with an example to show? It's hard to see. Timmy doesn't tell you he's doing that. He's just doing it on his own. And then much, much later you realize, what are you doing? Like, but you did it. I'm just doing what you did. Can we come up with an example where that rule doesn't work? So he is observing a rule that says A plus C over B times C equals A over B. That's what he's observing. Right? Is there an example for when that does not work?
5 plus 8 over 1 times
5 plus 8, there are many, right? Is there an example, another example that actually does work? Doesn't work in this question. So if I actually calculate that, that's 13 over 8, and not 5 over 1. It's ridiculous. Is there another example that actually supports Timmy's observation? Whew, that's a more difficult one. I haven't thought about that until right now. That's a good question. We're fairly intelligent people. We can come up with something. Is there another example?
Well, 4 plus 2 over 1 times 4 would be 8.
Okay, let's just swap them around.
So that would work, wouldn't it? Because 1 times 4.
You would then want to cancel the 4,
Yeah.
which gives
Would
you
that not-
2, but this is
Oh,
6
right,
over.
no.
Oh, you can make that 4.
I was trying to find something that wasn't doubles on the top.
I know, I think that's the key.
Yeah.
Yeah, I think that's the key. Not that there isn't another one, but it might be really hard to find. Yeah, the doubling of the number. But he doesn't see that, right? He doesn't know. Oh, it's only when these numbers are the same. It happens to be the same as this one. Gotta get it 2. He takes it even if they're not the same. You would continue that rule incorrectly. So it's very important they're all about self-discovery and making those connections and patterns on their own. But without the right guidance, that is just a disaster waiting to happen. And it does happen. All the time. Over and over. It's important to guide them to the right conclusion. Last one. Comparing fractions. I know we're almost done. I hear the packing up noise. Very subtle, very subtle. For example, I want to compare 2/3 and 3 over 4. Which one's bigger? So here I either want to have an equal, or I want to have a less than, or I want to have a greater than. Now Timmy knows what this means because the crocodile bites the bigger one because he's hungry. But you have to.
I have to remember that every time. I can't remember.
It's surprising how that sticks with so many people. It's very surprising. I don't remember if that's what they did for me. I don't remember. Can't remember if it was a crocodile or something. So we have to compare these. Now, even if you draw them, unless you draw them really accurately, you can't be sure, and Timmy's not going to draw them very well. Unless he's a future artist, it can happen. But you can't always tell. Maybe his fourths are a little out of sync, and it looks almost simpler. So you can't trust that alone. And it's because these denominators are not the same. They're not the same. So what if I make this fourths sideways and thirds sideways? That is going to help because now I'm counting 12s in both. So this is 1, 2, 3, 4, 5, 6, 7, 8, 8 12s. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 12s. It's like comparing apples to oranges. It doesn't work. But these are both apples, or both oranges, whatever you like. And you can clearly see that this quantity is bigger than this quantity. Crocodile is hungry, he wants to eat that. So, how do I get that without a diagram? This is simply 2/3 multiplied by 4 on both sides, which is exactly what we did. Here I had 3 over 4, and I multiplied by 3 on both sides, which is exactly what we did in the diagram. But I'm not restricted to a diagram. If I have my 3 and my 4, how do I get 12? What is 12 of 3 and 4? Previous section, 3 points. Ooh. I want to say 3. You're like, I wrote the quiz, I'm done, I don't remember. Least common multiple of 3 and 4. And then they call it, because it's the denominator, they'll call it the, is it the least common denominator? No, that doesn't sound right. You just look for a common denominator. Any common denominator would work. But usually if you keep it small, then it becomes more manageable. All right, I think that's a fairly thorough introduction, covering all the little things. What's next? What's next is we have to just look at the 4 operations a little more closely. Then we'll get a little mathy and talk about rational numbers, which is the fancy word. We'll talk about decimals. We'll talk about percentages. And we'll talk about variables a little bit. Because for most problems, I can't stay on that intuitive side. I need tools to help me move over and solve problems. But one thing at a time.